Right. Good evening, students. In the last class, we have started discussion on properties of mixture of gases, and then we have completed our discussion on Dalton's law of partial pressures. Now, let us look at the internal energy concept, enthalpy concept, specific heat, and entropy concepts in this particular class. Now, let us quickly review what we have seen in the previous class. Essentially, the summary of the previous class is shown in this form. So, if you take the pressure, the total sum of the partial pressures will be equal to the total pressure of the mixture that we have seen. And this concept we have seen on the volume. We already know this. The volume will be the sum of the remaining volumes of the individual gases, and the R, that is the particular gas constant or the characteristic gas constant, has to be measured in this fashion in terms of m. So in the numerator you will have the product of m and r for the individual gas, and you have to take the sum of all of that, and in the denominator you will be having the sum of all the masses. That's how you will calculate the r value, that is the characteristic gas constant value for a mixture, and then n, that is number of moles, will be calculated, or the kg mole we say, as a sum of all the individual gases that is present in the mixture. Same is the case with the mass. So these are the things we have seen. We have also seen that the R formula is nothing but R bar by the molecular weight, and the same can be written as R bar equal to R into molecular weight. These are the few things that we have seen in the previous classes. Also, we have seen the concept of the mole fraction and so on. So these concepts we have seen. In continuation to that, today we will be looking at the concept of, let me write it here, internal energy of gas mixture. So this concept we are going to see today, the internal energy of the gas mixture. That's the concept that we are going to see now. So for understanding this internal energy of a gas mixture, we will be looking at the Dalton's law in an analogous manner. Analogous to Dalton's law, we can write that total internal the total internal energy will be equal to the sum of internal energy of each gas. Total internal energy is nothing but sum of internal energy of the each gas. It is like the total pressure of the mixture is equal to the sum of the partial pressures, right? That's what we have seen in the Dalton's law. Similar to that, we have the internal energy concept here, their pressure, and here we have internal energy. So the same expression can be written mathematically in this form, like we can write U of the mixture equal to U1 plus U2 plus so on plus UC. So here I have used the capital U, meaning that my U is measured in terms of kilojoules. Okay, that's the unit of U here, that is a kilojoule is the unit. The same thing if I write in terms of kilojoule per kg, what I have to do? The U will be equal to mass into small u, so that the mass is measured in kg, and u, that is specific internal energy, is measured in kilojoule per kg. So I can write the U of mixture as mass of the mixture into the specific internal energy. The capital U is now becoming the small u here. So small u of the mixture will be equal to m1 u1 plus m2 u2 plus so on plus mc uc. So that's what we have here for the various gases. That is, simply put, in the place of capital U, you have written small u into capital small m. Sorry, u, the capital U is equal to m into u, mass into the specific internal energy. So that's how you have transformed this equation. The specific internal energy um can now be calculated in terms of m1 u1 plus m2 u2 plus so on plus mc uc by m is nothing but m1 plus m2 plus so on plus mc. Okay, this formula also we have seen in the summary of the previous class. So this is what we have here for UEM. Right. So um is equal to, in this fashion, we can write the internal energy of a gas mixture. This is how we will find out. And based on this U, you can get CV of the mixture as well. That is a specific heat at the constant volume. So how do we get that? Since du is equal to CV into dt, for same dt, we can write the du is proportional to CV. So from that we can write the, in place of u we will get CV now. The CV of the mixture will be equal to m1 and CV of 1 plus m2 into CV of 2 plus so on plus mc into CV of c divided by m1 plus m2 plus so on plus mc. So this will be the expression for my CV of the mixture, that is specific heat yet constant pressure. Specific heat at constant pressure. Sorry, it's not constant pressure, it's constant volume. I'm sorry, this is not constant pressure, this is constant volume. CV is constant volume for gas mixture. For gas mixture. So we got two formulas so far. We got formula for U and we got formula for CV. Okay, so if you look at this CV formula here, the M is measured in kg and the CV will be measured in kilojoule per kg Kelvin. Whereas here in this formula, M will be measured in kgs and the U will be measured in kilojoule per kg. So that's the difference here. Per Kelvin you will get here. Per Kelvin you will get here. That's the only difference. Otherwise more or less the same thing. And you can also compare this CV expression with your R of the mixture. So if you look at the R of the mixture, this is nothing but M1 into R1 plus M2 into R2 plus so on plus MC into RC by M1 plus M2 plus so on plus MC. So This is a formula for your RM as well. So if you look at the unit balancing here also, you will have in this case, so I have written these two for this formula, the CV formula, and this for RM formula also you will have the M in the similar manner. M is kg, and the R value will be in kilojoule per kg Kelvin. That is, both your CV formula and R formula are again analogous here. Okay, so that's what we can see from the story of internal energy of the gas mixture. Now that we have seen the internal energy of the gas mixture, we will now move on to the discussion of enthalpy of the gas mixture. Enthalpy of gas mixture. So this is the concept here. Again here we can take the analogy of the Dalton's law, analogous to Dalton's law of partial pressure. We can write that the total enthalpy of mixture of gas mixture, to be specific, of gas mixture will be equal to the sum of enthalpy of each gas. So if I put that mathematically, that will become H of the mixture will be equal to H1 plus H2 plus so on plus HC. This being measured in terms of kilojoules. The same thing now, if I write in the terms of kilojoule per kg, since H is equal to M into small h, that is the enthalpy is nothing but the product of mass into the specific enthalpy, where M is measured in terms of kg and small h, that is the specific enthalpy, is measured in terms of kilojoule per kg. I can write that H mixture is nothing but M into H, and here in place of H1 I will get M1 H1, in place of H2 I will get M2 H2 plus so on plus I'll get MC HC. So if I want the H of mixture now, HM equal to M1 H1 M1H1 plus M2H2 plus so on plus MCHC by M I will get, which is nothing but M1 plus M2 plus so on plus MC I will get. So that is the expression for your HM, that is enthalpy of the mixture of gases. So from this we can now connect this to Cp, because since your dH is equal to Cp dt, for same dt, for same dt, there is a temperature change, I can write that dH is proportional to Cp. So analogously, if I take in place of H, I can put Cp now. So the Cp of mixture will now be equal to M1. In place of H1, I have to put Cp1. M2. In place of H2, I have to put Cp2 plus so on plus Mc into Cpc by M1 plus M2 plus so on plus Mc. So this is what I can have for Cp of a mixture of gases. So also here I can have the units for this particular formula. The units will be m is nothing but in kg, and the Cp will be measured in kilojoule per kg Kelvin. And also I can write that this is a formula for specific heat at constant pressure for gas mixture. So now I got the formula for enthalpy and the CPM. Okay, the enthalpy formula for gas mixture and CP formula for the gas mixture. Even this CP formula for the gas mixture can also have the analogy with your R. Again here, like I have discussed for CV, I can discuss even for CP here. So it is nothing but M1R1 plus M2R2 plus so on plus MCRC by M1 plus M2 plus so on plus MC. So that is a formula for your RM. It is also similar to your it is also similar to this previous discussion that I have already discussed regarding your CV. Like you have this M in kg and the Cp in kilojoule per kg Kelvin. The same is applicable here as well. Okay, so both will have the same unit. The Cp and R will have same units because Cp minus Cv is equal to R by definition. Since Cp minus Cv is equal to R by definition, both will have the same units. So you will have similar formulas for R for the gas mixture and Cp for the gas mixture, and correspondingly the internal energy and enthalpy will also have the similar formulas here. Okay, and one more concept that we should see in connection to this is the entropy of gas mixture. So the entropy of the gas mixture is little bit different compared to all other formulas you have for the mixture here. So here the S of the mixture will be defined in terms of your N, that is the kg moles. So N1S1 plus N2S2 plus so on plus NCSC you will have, where N is the number of moles for each gas measured in kg mole. Kg mole should be the unit here, and S1, or I should say S is the entropy of each gas measured in kilojoule per kg Kelvin. So here you will take the N1, N2 and NC, and you may ask me the question, how did I get N1, N2, NC? Why did I get this? So this is basically derived from something called as a Gibbs theorem. Gibbs theorem gives us this correlation. Like your Dalton's law of partial pressures gives you the previous formulas, here you will make use of the Gibbs theorem to get this expression, that is S mixture will be equal to the N1 into S1 plus N2 into S2 plus NC into SC. This formula you will be getting based on the Gibbs theorem. So these are the various formulas that we have in the entropy, not just in the entropy, it's regarding all the gas mixtures. These are the various formulas that you're going to have. Now, based on this, we will solve a problem here. So let us take up this problem and solve it. So for various formulas that we have here, this problem will be of great help for us. And let us solve this particular problem here. And this problem has so many parts in this. Somehow that parts are not coming here. Let me type them. So I think the question is clear now. So here goes our question. And in this question, there are about A, B, C, D, H till H you have questions. So we need not worry about these many questions. The idea of having this question is covering the various kind of questions that you may get based on the similar questions. They are all simple, nothing to worry about. Just follow through, you will be able to understand. Here we have a mixture of gases. So, and maybe you can probably consider a box like this, and in this box you have two gases here. So the first gas you have here is nitrogen, N2, and on the other side you have CO2. So you can read it out here. The nitrogen and carbon dioxide is the names of the gases here. These are the names of gases. So the N2 is given as 3 kg. Let me call the N2 as 1 in this question and CO2 as 2 in this question. So this will become M1, and the M2 value is also given in the question as 5 kg. And what else is given? The gamma 1 is given. So the gamma 1 is 1.4 here, and the gamma 2, which is nothing but the adiabatic index. Adiabatic index will not have any unit. So 1.286 is the value given to your gamma for the CO2. And here he has also given the pressure. So this is the pressure of the mixture he is giving you. So the pressure is actually given for the mixture, which is 300 kilopascal, and is also given the temperature here. This is also a temperature of the mixture. Although it is a temperature of mixture, you can take it as T1 is equal to T2 here, and let me call this as Tm. That will be 20 degrees centigrade. You have to convert it into Kelvin appropriately whenever it comes. So 20 plus 273 Kelvin you have to substitute every time you make use of the temperature here. And let us go to the first part of the question now. The first part of the question, A, is asking you to find out the mole fraction of the each constituent. So the question 1, he is asking you to find out the x1 and x2 values. That is the thing he is asking you to find out. And we know that the formula for x1 is equal to the n1 by n1 plus n2, and also we know the formula for x2 is equal to n2 by n1 plus n2. How did we get this? Basically, if you write it for xk is equal to nk by sigma n we have written. Okay, this formula we have already written in the previous classes. So based on this formula we get these formulas here. So they are simple conversions there, and in order to find out this x1 and x2 you should first know the values of n1 and n2. So how do we get the values of n1 and n2 here? So the n is equal to mass by the molecular weight. We know this formula, most regular formula. N1 I am writing here, I will use m1, so molecular weight of 1. So 1 is nothing but my nitrogen in the question. So for nitrogen the mass is given as 3 kg, and the molecular weight for the nitrogen should be remembered by hearted by the student, which is nothing but 28 kg per kg mole. So this value will be measured in kg mole now. because the kg in the numerator and the denominator will get cancelled, and the N2, same formula, M2 by molecular weight of the 2. The M2 value is given as 5 in the question. Here we can see the value is 5, and the molecular weight of the carbon dioxide must be by hearted by the student, which is nothing but 44 kg per kg mole, and kg in the numerator and denominator goes, so the value 5 by 44 will have the unit of kg mole, which is nothing but the unit of N. So that's appropriately fitting there. And then now you can find out the x1 value. So the x1 value is nothing but 3 by 28 in the numerator by 3 by 28 plus 5 by 44. So that will give you a value of 0.485, which is nothing but the value of x1 he is asking you to find. So we have able to find the value of the x1, 0.485. That is the x1. So you're done with finding x1, and you should also find out x2. So for finding out x2, the n2 by n1 plus n2, so that will be 5 by 44 in the numerator divided by 3 by 28 plus 5 by 44, that is n1 plus n2. So that will give you a value of 0.515. So you are able to find the x2 also now, that is 0.515. So the first part of the question is done. Is asking you to find out the x1 and x2. You are able to find out the x1 and the x2 values, and you can also identify, you can also cross check that this x1 plus x2 values are equal to 1. Okay, so if you add these 485 and 515, we will get 1000, right? So 0. This much will be 1. Okay, because 3 decimals will get you that 1000. So x1 plus x2 value will be 1, and this condition also is getting fulfilled. So this way you can cross check the values that you got, because there are only two constituents or two gases in this mixture. So you will be taking x1 plus x2. Let's say there are 3 gases, you will take x1 plus x2 plus x3, so on like that you will be taking this. And it's always good to cross check based on these expressions as well, that is x1 plus x2 plus x3 plus so on is equal to 1. Always try to cross check your values with this expression as well. That will make sure that you are solving it in the right direction. Now we will go to the question B. The question B is equivalent molecular weight of the mixture. Equivalent molecular weight formula we have already seen. The equivalent molecular formula, we have written it like this. Is asking you to find, let us write that first, and then the formula we have seen is in terms of x1 into the molecular weight 1 plus x2 into molecular weight 2. So you got the x1 value with you, which is nothing but 0.485 into the molecular weight of the 1, that is nothing but your nitrogen, which is 28, and the x2 value you got as 0.515, and the molecular weight of the 2 is nothing but the molecular weight of the carbon dioxide, that value is 44. You can substitute that. So the molecular weight of the mixture will turn out to be, you calculate that and you will get this value as 36.25 kg per kg mole. That is the value of your equivalent molecular weight or the total molecular weight of the mixture. This is how you will find. So you are done with the question B here. Question B is done, and then question C, equivalent gas constant of the mixture, means he is asking you to find out the characteristic gas constant value R for mixture. That is the question. This formula we already know. R mixture is nothing but M1R1 plus M2R2 by M1 plus M2. So since there are only two things here, two gases here, I have written it for two gases. If there are more gases, you can extend this accordingly. Let me correct this here. This has somehow gone wrong here. Plus M2. So that is a formula here. So you have M1 value as 3 kg given in question, M2 value as 5 kg given in question, and you need R1 value here. R1 is nothing but the R value of your nitrogen. So you can write as R bar by molecular weight. The R bar value is 8.314 and the molecular weight of the nitrogen is 28, and R2 you can get as R bar by molecular weight. Similarly, the R bar value is 8.314 for every gas because it is universal gas constant, and the molecular weight of the carbon dioxide is 44. So now you have everything that is required for this formula, and you can just substitute that 3 into 8.314 by 28 plus 5 into 8.314 by 44 by 3 plus 5. So that will give you the R of the mixture as a 0.229. Sorry. 0.229 kilojoule per kg Kelvin. 0 per kg Kelvin is the Rm value that he is asking you to find out. So you have found out the C question, the R mixture value is done, or the equivalent gas constant you have found out. That part is done. And the next question is partial pressures and partial volumes is asking you to find. So in the question D, you have to find out what is the P1 value and what is the P2 value, and you have to find out the volumes also here. The volume is V1. What is V1 and V2? That's the question here. Let us find out the partial pressures initially. The partial pressure P1 is nothing but X1P. So P being the total pressure. So the X1 value we have found out in the first question itself. That value is 0.485 and the P value is 300 kilopascals given in the question. So P1 will be now equal to 145.5 kilopascal. That is the P1 value that he is asking you to find out. So P1 is done. Now we will move to the P2. P2 is nothing but X2P. The X2 you know as 0.515 into the P is 300 kilopascals that is given in question. So the P2 value will now be equal to 154.5 kilopascal. So you got P1 and P2 values now. So that part is done, and you have to do V1 and V2 values. So in order to do the V1 and V2 values, we can make use of this formula that we have used for volume. V is equal to V1 plus V2 plus so on plus Vc we have done. So while doing that, we have taken that PV1 is equal to M1R1T. We have taken the P that we have written here. I am directly taking this P and writing it here in the denominator. Similarly, I will write it for V2 as well. M2R2T by P. So this is the these are the formula for V1 and V2. So we can substitute the things appropriately here. You have 3 as a M1, R1 is 8.314 by, since the R1 is nothing but your nitrogen, you can substitute the molecular weight 28 here, and the T value is 20 plus 273 as substituted in Kelvin. 20 degrees centigrade is given in the question. The P value is 300 kilopascals given in the question. So that will give me the V1 value of 0.87 meter cube. That will be my V1 value for the nitrogen. Now I can also go to the calculation of V2 now. So if I go to the calculation of V2, the V2 will be, the M2 value is given as 5 in the question, and the R2 value is 8.314 by the molecular weight of the CO2 is 44, and the T value here is 20 again, plus 273 divided by the pressure is 300 kilopascals given in the question. So I can substitute that. That will give me V2 value of 0.923 meter cube. So that will be my V2. So I'm done with my P1 by P2 and V1 and V2. So I'm done with the question D now. Question D is done. From A, B, C and D we have completed. Now we will look at E. So the volume and the density of the mixture he is asking us. So the volume, if you look at the volume is again simple. This is the question E. The question E is asking the volume of mixture. Also is asking you to find out the density of the mixture. So V of mixture is simple. It is nothing but V1 plus V2. You can do it directly. Otherwise, you can do using one more formula, that is V of mixture will be equal to M into R into T by P, where you have this M as 3 plus 5, which is 8, and the R value you have found out in the question question C, I guess. It is 0.229, and the temperature value is 20 plus 273, you know it, by the pressure value is 300 kilopascal, you know it, and you can get the V of mixture value. This is one way of doing it, and this V1 plus V2 is a simpler way of doing it. That is 0.87 value you got previously, and the V2 value also you got previously, that is 0.923. So both ways you will get the same answer. V of mixture will be equal to 1.79 meter cube. So that is the VM that you are going to get in both the cases. Okay, both the ways. So we are done with the VM calculation, and he's asking you to calculate the rho also. So rho also you can calculate it from the basic formula of rho. So the rho formula, density formula, is nothing but mass by volume. Mass of the mixture you can take, and volume of the mixture you can take. The mass of the mixture is 3 plus 5, that is 8 kg, and the volume of the mixture just now we have found out as 1.79. You can substitute that. So that will give you the rho of mixture. Rho of mixture will be equal to 4.46 kg per meter cube. So that's the rho m. So we're done with the question E. Now let us go to the question F. In the question F, he's asking you to find the Cp of the mixture and the Cv of the mixture. So the question F. If you go here, what is asked you to find a Cp and the Cv. Here he is asking you to find out the Cp value and the Cv value for the mixture. If you go with the Cp formula, the Cp will be equal to m1 Cp1 plus m2 Cp2 by m1 plus m2. So in this, I know that the m1 value is 3 kg and the m2 value is 5 kg, and I should get the Cp1 value and the Cp2 value here. The Cp1 is nothing but the Cp of nitrogen, and the Cp2 is nothing but the Cp of carbon dioxide. So if I have to calculate this, the formula that we have here is gamma r by gamma minus 1 is the formula for Cp. The same formula I can use here, gamma r. It's not gamma minus r, it's simply gamma r. Gamma r by gamma minus 1. So here you can use gamma 1 r 1 gamma 1. So here you can use gamma 2 r2 gamma 2. So the gamma 1 value is given in question as 1.4, and the R1 value is nothing but 8.314, the universal gas constant by the molecular weight 28 by 1.4 minus 1. So that will give me a value of 1.039 kilojoule per kg Kelvin. Similarly, you can substitute the values of Cp2, which is 1.286 into 8.314 by 44 by 1.286 minus 1. 1.286 minus 1. That will give you a value of 0.85 kilojoule per kg Kelvin. So now you can substitute these values into the Cp expression. You will get that as 3 into 1.039 plus 5 into 0.85 plus 3 plus 5, which will give you a value of 0.92. So the Cp of the mixture will be equal to 0.92 kilojoule per kg Kelvin. So this is a Cp of mixture story, and now we can now move to the Cv of the mixture. So the Cv of mixture, if you see, the formula is m1 r1, sorry, it's not r1 here, Cv1 I should say, which is similar to r also, Cv1 plus m2 Cv2 by m1 plus m2. So you have the m1 value 3 kg, m2 value 5 kg with you, and you need Cv1 here, and you also need Cv2 here. Cv1 is nothing but the Cv of the nitrogen, Cv2 is nothing but the Cv of the carbon dioxide given in the question. So the formula for finding out Cv is R by gamma minus 1. I should write this clearly, gamma minus 1. Here also I will have R by gamma minus 1. So this will be for R1, this will be for R2. This will be for gamma 1, this will be for gamma 2. So the R1 value, you may know the story, 8.314. By, since nitrogen we have 28 is the molecular weight, and the gamma 1 is given in question as 1.4 minus 1. And here the R2 value is 8.314 by 44 by 1.286 is the value given for gamma 2. So I can substitute those values here. If you calculate, you will get the CV1 as 0.742 kilojoule per kg Kelvin, and the CV2 as 0.661 kilojoule per kg Kelvin. So that is the CV1 and CV2 value. So now you have everything for CV mixture. So the M value is 3 and the CV1 is 0.742 plus 5 into 0.661 by 3 plus 5, which will give me the CV of mixture as 0.69 kilojoule per kg Kelvin. So that's the value of CV of the mixture for you. So we're done with the CP and CV of the mixture. So we're done with the F part of the question. Now we will move to the G part of the question. In the G part of the question, he is asking you to find out the changes in the internal energy, change in enthalpy, change in entropy of the mixture if the mixture is heated to a constant volume, heated at constant volume to 40 degrees centigrade. So far we have used only T, which is T1, we can say now T1 as 20 degrees centigrade, and now he has added T2 into the question, which is 40 degrees centigrade. And based on this, he's asking you to find out what is U2 minus U1. Also, he's asking you to find out enthalpy, H2 minus H1. Also, is S2 minus S1, that is entropy. So these are the things he's asking you to find out. So let us look at this now. This is G part of the question. The G part of the question, if you have to find out U2 minus U1, see, U will always depend on your CV. So since I am writing capital U here, I can write M also here. If I am writing small u, I need not write M here. So since I am writing capital U here, M, I am writing here M into CV, I will get, anyways, du is equal to CV dt. I know du is equal to CV dt. So I can write CV here, and the temperature difference is T2 minus T1. I know that. So the M value is 3 plus 5, 8 kg. Into the CV value just now we have found out in the previous question, it is 0.69, and then T2 is given as 40 degrees and T1 is given as 20 degrees. You can add plus 273 also here, but on the other side you have minus 273, both will get cancelled. So whether you substitute it in Kelvin or degree centigrade doesn't make any difference. That's why I'm directly substituting it in degree centigrade. If you want to substitute it in Kelvin also, it doesn't make any difference. So you will get the U2 minus U1 value here. That value will be 110.4 kilojoules. That's the difference in internal energy he's asking you to find out. Also, he's asking you to find out difference in enthalpy, H2 minus H1. So we know that dH is equal to Cp dt. So similarly, I can have M here. Since I'm using capital H here, I will have M Cp into T2 minus T1 I will have. So M is 3 plus 5, known story. And the Cp you have found out in the previous sub question, that is 0.92. What happened here? This is nothing but 3 into 40 minus 20 you can use, so that you will get the H2 minus H1 value equal to 147.2 kilojoule. That will be my difference in enthalpy. So H2 minus H1, I will get this much. Also, is asking you to find out the S2 minus S1 here. So the S2 minus S1 formulas, if you remember, there are S1 formula, S2 formula, and S3 formula. So there is forms of this S2 minus S1. So here M CV into ln T2 by T1 plus M into R into ln V2 by V1. I will take this formula here. So in this question, he is giving that is the constant volume process. If it is heated at constant volume, he said in the question. So since V2 is equal to V1, that will imply ln of V2 by V1 will be equal to 0. Since this is equal to 0, I can equate this complete term to 0. So now my S2 minus S1 will become S2 minus S1 will be nothing but MCV into ln T2 by T1. So the M value is 3 plus 5 in the question. And the CV you have found out in the previous sub question. The value is 0.69 and the ln is given as 40 plus 273 here and 20 plus 273 are the values of temperature here, so that it will give you S2 minus S1 equal to 0.368 kilojoule per kg Kelvin. So that is the S2 minus S1 he is asking you to find. So you have found out all the things he is asking. You have found out the change in internal energy, change in enthalpy, and change in entropy. That's the part of question G. So you're done with question G. Now we'll move to the question H. Find the changes in internal energy, enthalpy, and entropy of the mixture if the heating is done at the constant pressure. Okay. So the same question, the same T1 and T2, for same T1 and T2 is asking what will be the values of all the things if there is a constant pressure process. If there is isobaric process, what will be the case he is asking. So in that case, your internal energy and enthalpy is going to be the same. Okay, so it is going to be the same like you have done here. So this will be your U2 minus U1. This will be your H2 minus H1, because this U2 and H2, that the change in internal energy and the change in the enthalpy will not vary for a constant pressure process and a constant volume process. Only change in enthalpy will vary. So you have to find out the enthalpy only here. For the remaining things, you can directly write the values here. This is question H. The U2 minus U1 is MCV into T2 minus T1. We have already calculated it previously, which is 110.4 kilojoule, and H2 minus H1 is equal to M Cp into T2 minus T1, which is 147.2 kilojoule. These things we have already found out. Now you have to find out what is the value of S2 minus S1. For this S2 minus S1, for a constant pressure process, you take it the MCP. You should not take it in terms of CV now. You should take it in terms of CP, because this is a constant pressure process. MCP into ln T2 by T1 you have to use, and the R should be used in the other formula, other part of the same formula. MR into ln P2 by P1. This is the S2 minus S1 formula that we already know. Since this is a constant pressure process, P2 will be equal to P1. The P2 will be equal to P1. That will imply logarithm, that is ln of P2 by P1 will be equal to 0. So that's why this term will get equated to 0. Now your S2 minus S1, I'm sorry, somehow it is getting changed. The S2 minus S1 is now mCp into ln T2 by T1. So the m is 3 plus 5 we know in the question, and the Cp you have found out in the previous sub question 0.92, and the ln T2 is nothing but 40 plus 273, and T1 is nothing but 20 plus 273. So that S2 minus S1 will be equal to 0.49 kilojoule per kg Kelvin. So you have found out S2 minus S1 even in the constant pressure process. So this question that you have solved here is a more comprehensive question which covers all kind of things that you may get in the properties of gas mixtures. So this kind of questions generally you will get. So I think with this we have completely seen the syllabus of this particular unit. Sorry, not a particular unit, the sub part of this unit, that is properties of gas mixtures, we have completed. So we will see the thermodynamic relations in the next class. Thank you.